We're looking at what momentum is, understanding why we want to know about it, understanding why its vector nature is vital to the work we're going to do, and the conservation of momentum when it is and isn't conserved. So, let's consider two masses. Let's say these two masses are the same. Let's say they're both tennis balls. And let's say those tennis balls are moving with different velocities. Let's say that the top ball is moving with, let's say, 5 meters per second. And the bottom ball moving with maybe 10 meters per second. Now, if these two tennis balls were to hit you, you would know which one was traveling faster. This one would hurt you more than this one. And so the force applied by these tennis balls, because it is the force primarily that's causing the pain, the force applied depends on the velocity of the tennis ball. So let's then consider two different masses. Let's say these two are traveling at the same speed. And let's say one is, let's say they're both traveling 20 meters per second. But let's say this is a tennis ball, so as before, but this is a cannonball. So my point is that the mass of this one is maybe 50 kilograms, and this one is maybe, I don't know, 30 grams, so 0.03 kilograms. So despite the fact that they are traveling at the same velocity, this one will do a lot more damage than this one. So the point to that is that there are two factors that affect the damage that something might do. Our first factor is the velocity. So two factors affect the impact, let's say, of an object. Now there's more than two. You might start thinking about the shape and the pressure, but if we set those to one side for the moment, two factors affect the impact of an object. One, the mass in kilograms, and two, the velocity. Now notice I'm talking about velocity, not speed. That's not coincidental. So what we're talking about then, if we combine these two, m and v, is the product of mass and velocity. That is to say, momentum equals mv. And the symbol we use for momentum very often is p. So momentum kind of captures the mass effect and the velocity effect of a moving object. So if it's not moving, it's got no momentum. The larger the mass is, the more momentum it'll have for a given velocity. The larger the velocity is, the more momentum it'll have for a given mass. So it's not a very satisfactory definition. Momentum is the product of mass and velocity, but you can see how it captures these two things that affect the impact that an object will have, or indeed how difficult it is to change its motion. So, moving on from that then, let's consider an example. So, let's say that we have this object moving. Let's say that's 1 kilogram at 1 meter per second, and it collides with 1 kilogram which is not moving. And afterwards, these two move off together. So let's say they've stuck together. Now, we say that momentum is conserved. Like energy, momentum is conserved, but only if no external forces act. Now, if you think about it, external forces, friction, gravity causes an external force. So, if you think, where could I go? What situation could I consider where there are no external forces? And actually, if you think about it, you can't think of any situations where there are no external forces. So what we're talking about in practice is external forces which are so small they don't actually materially affect what we're working on. So we'll say momentum is conserved, and then we'll say, well, actually there's friction here, and so momentum isn't quite conserved. Things are not going to be quite as we calculate. So this is the principle of conservation of momentum. That momentum is conserved if there's no external forces acting. What that means is the momentum before an event equals the momentum afterwards. So here we've got momentum of this object, which is 1 times 1, mass times velocity, plus 0, because this has no velocity, equals 2 kilograms, because this is behaving like 2 kilograms, times whatever the new velocity is of these two. Right? So we have 1 equals 2 times v, which leads us to v equals 0.5 meters per second. Oops. All right. So, we have taken this direction as positive. So, there are no velocities going to the left, so that's all nice and simple. To the right is positive in this example. So let's now consider two objects moving in the same direction. Let's say we've got one kilogram, 1 meter per second. And we've got, let's say 2 kilograms moving at 0.5 meters per second, because I want this one to catch up with that one. And then let's say together afterwards we've got our 1 kilogram and our 2 kilograms stuck together, and we end up with some velocity again. So momentum before, if I use P to save me writing out momentum, equals momentum afterwards. We've got 1 times 1 plus 2 times a half will equal 1 plus 2 is 3 times V. So we've got 1 and 1 is 2. 2 times a half being 1 is 3 times the velocity. So the velocity then would be 2/3 meters per second, or 0.67, because in physics anyway we don't leave things as fractions. 0.67 to two significant figures. You might say, I've only got one sig fig in my data, so 0.7 meters per second to 1 sig fig. So let's look at a further example then. Let's look at exemplar 3. We have two objects moving in opposite directions. So we have our surface. This is where the vector nature is really important in our calculations. So let's say we've got 1 kilogram moving at 1 meter per second. And we've got our 2 kilograms moving at 1 meter per second. Indeed, I could have the same example as before, 0.5 meters per second. Let's use the same numbers. 0.5 meters per second and 2 kilograms there. So, like before, momentum before equals momentum after. So we have 1 times 1, but this time that's going in the opposite direction, equals, minus 2 times 0.5, because if this is positive, then that's negative. So 1 times 1 minus 2 times 0.5, and, well, let's just say they stick together again. There's my 1, there's my 2. So 1 times 1 minus 2 times a half is our 3 times V. Well, here you see 1 minus 1 is 0. So our velocity will be 0. These two colliding, if they stick together, will stop. The momentum of this one exactly cancels the momentum of that one, if you like. Or the total momentum before the collision is 0, because I've got 1 in this direction and 1 in that direction. And let's just look at the units of that, because it's uncomfortable talking about numbers without units if they deserve units. So we are multiplying mass by velocity, mass is in kilograms, velocity is in meters per second. So that is kilograms meters per second. Now if you look at your Newton's law, Newton's second law, you'll see that that looks quite like Newton's. It is Newton seconds. So two possible units for momentum, kilograms meters per second or Newton seconds. So you see how the vector nature, the fact that momentum is a vector and has direction, is really important in our calculations, because with the same numbers as we had in exemplar 2, the answer is very different, because in this example the 0.5 meters per second is to the left, not to the right. So that's exemplar 3. Let's look at exemplar 4 then, an explosion. So let's consider, let's say, a hand grenade, a nice spherical hand grenade. So this is sitting on the desk. It has no momentum. Clearly, its velocity is 0. Afterwards, of course, after it has exploded, you're going to have a bit going this way, and a bit going that way, and a bit going that way, and a bit going that way, and a bit coming out of the board, and a bit coming into the board. So in every possible direction, there's going to be bits. Now, since the momentum is 0 here, the total momentum here must be 0. Nobody's going to argue that these bits don't have momentum. But the total momentum will be 0, which means for every bit that goes that way, there has to be a bit that goes this way, and the momentum of those two will add to 0. And along this line, the momentum of these two will add to 0, and the momentum of these two will add to 0. So the total momentum remains 0 before and after. So if you said that this bit had a mass of, let's say 10 grams, or 0.01 kilograms, and let's say it's traveling with a velocity of 300 meters per second. We could then say, if we knew the mass of this bit was 0.02 kilograms, we'd be able to say, well, along this line, because momentum is 0 here, momentum will be 0 here after the event. So momentum before 0.01 times 300 will equal 0.02 times the velocity of this bit. So 0.01 times 300, that's 3 kilograms meters per second, is 0.02 times v. So 3 divided by 0.02, that's 3 times 100, divided by 2 is 150 meters per second. So you see that the momentum along a line, because momentum is a vector, because there was no momentum to begin with, there can be no momentum along this line afterwards either, which means that the momentum of this bit equals the momentum of this bit in the opposite direction, minus that momentum. And so bigger bits will be travelling more slowly. So that's how you deal with an explosion. So you've seen one object moving, one object stationary, both objects moving in the same direction, objects moving in opposite directions, and something which begins with no momentum, and how to deal with that. All of this then relying on your application of momentum being a vector. So Let's consider our summary then. We have momentum is mass times velocity. Momentum before an event equals momentum after an event. If we have no external forces, like friction or weight, for example. It could be magnetic, could be electric, any force which is outside of the system. So the forces in the explosion, for example, they were internal forces because there was a force created by the object itself, as opposed to friction, which is between the object and the surface it is on. So we have momentum as a vector. Which means it has direction. And the units are kilograms meters per second or newtons seconds. Now, if you think about going back to Newton's second law, we'll come back to this in another video, but Newton's second law, F equals ma, that is newtons, of course, for force, kilograms, and meters per second squared. Now, this is kilograms meters per second, so this is this multiplied by seconds. So kilograms meters per second squared times seconds would have to equal newtons seconds, and that's how you end up with that. So there's your summary so far. Now let me point out to you some examples that you could do. You could go to Grade Gorilla. This is a great little multiple choice micro quiz for you. So if you go there and have a go at that, if your teacher is signed up to it, then they can give you your marks, and it's a really quick, handy way of checking your progress and your grasp of this stuff. And once you've done that, you can go to Isaac Physics. There's some good challenging questions there. But before we do that, let me take you to do this. So, a gun fires a bullet with a mass of 0.1 kilograms. 0.01 kilograms, sorry, at a velocity of 200 meters per second. What is the momentum of the bullet? Well, momentum is mass times velocity, which is 0.01 times 200, which is 2 Newton seconds. The gun has the same momentum as the bullet, but in the opposite direction. Explain why its velocity is less. Well, momentum is conserved. Of course. So, momentum before equals momentum afterwards. Momentum before, of course, before you pull the trigger, is 0. Equals the momentum of the bullet plus the momentum, momentum of the gun. Now, since the gun has a much greater mass, it must have a much smaller velocity. So, easy enough. So, go back then to Isaac Physics and Grade Gorilla and have a go at those questions and any other questions that perhaps your teacher has set for you. So just to remind you, there's your Isaac Physics questions, and there's your Grade Gorilla questions. And what we were trying to get across were these things. What is momentum? Product of mass and velocity. Why we want to know about it? Well, I haven't covered that really, but really what we're looking at here is all kinds of safety. We're going to come on to that because the momentum of an object dictates the size of the force you have to apply to stop it or change its motion. The vector nature, why is it important to us? Well, because the direction of the momentum makes a big difference then to the calculation that we do. And conservation of momentum, it is conserved when there are no external forces, but that's pretty much never. So what we're really doing is saying it's pretty much conserved where the external forces are so small as to not make a significant difference to our calculation.